Good evening, Erik Jensen speaking. It's a pleasure to be at the World Congress of Anesthesiologists, and thank you for the organizers and thank you for the invitation. And the title of my speech this afternoon is Processed EEG, the key to a nociception index. And this is a bit of summary. What you see on the slide, this is what I will talk about today, a bit about brain anatomy. Where do we find the signal which is related to nociception, the changes of EEG, the signal processing, and the implementation of all the data inside the Conox monitor. And I have to disclose that I'm the CEO of Quantium Medical, which is the manufacturer of a processed EEG monitor, the Conox, and Quantium Medical is part of the Fresenius Kabi group and the manufacturer of the Conox. And since this is an expert session, do feel free to interrupt me if you have questions in the middle of my presentation. Then I'm happy to enter into a dialogue. You don't need to wait until the end of the presentation. So what I first wanted to show here is a picture of the brain anatomy, and from where do we record the EEG when we put electrodes on the forehead of the patient. So most of the signal that we record is coming from the cerebral cortex as we position the sensors frontally on the patient. We do get some signal from lower subcortical areas as well, such as the thalamus or the insular cortex, which is important as well in terms of nociception monitoring. The natrium and kalium gated ion channels is what is generating the action potential. So this is what we can see here over the axon. We see a voltage charge, which is being sent from one end of the axon to the other. And this is basically what is creating the EEG. So when we sum all these impulses, summing up all these impulses will then give rise to a complete EEG. The electroencephalogram is the sum of billions of neurons spiked activity. So the single activity spiked, but when summing it up, we get a wide range of frequencies. If we compare the electroencephalogram with the electrocardiogram, then we can see that the amplitude of the electrocardiogram is much bigger than that of the EEG. So that means that it's also more easy to extract a heart rate or complete electrocardiogram from ECG than extracting features from the EEG. And we can already see here that ECG is much more periodic as compared to the EEG. The EEG contains lots of information. A lot of the information is hidden inside the EEG, so we need to use advanced signal processing methods in order to be able to extract the information from the EEG. The Conox Depth of anesthesia monitor applies a sensor with 3 electrodes on the forehead of the patient, where we record the EEG. We then extract the EEG spectral features, burst suppression, important parameter as well. And from that, we derive the qCon index, which is our index of hypnotic effect, and the qNOX, which is the index of the nociception, anti-nociception balance. So here, important to explain that both indices are extracted from the same EEG. So from one sensor, we are able to estimate both the hypnotic effect and the nociception balance. So the EEG changes at the anesthesia plane. So when a patient is awake, we have a fast EEG, higher frequencies, which corresponds to a high value of the qCon. And as the patient is sedated, the qCon is dropping down and the waves of the EEG is gradually getting slower. When we get into an anesthetized EEG, then we have an almost periodic EEG. It's not a sine wave, obviously, but it's quite clear that the complexity of the EEG is much less when the patient is anesthetized as compared to the awake state. Obviously, in the awake state, we have a high entropy, we could say, a high disorder of the signal, and that is one of the processing methods of EEG, is to look into the complexity of the EEG, see what is the difference in complexity while the patient is awake versus when the patient is anesthetized. When we get into deep anesthesia, then the pattern of the EEG is changing dramatically. We get burst suppression. So burst suppression is defined as periods of suppression, which is an isoelectric EEG, almost flat EEG, and then superseded by bursts. And these bursts are thought to be the thalamus, which is trying to wake up the cortex. It does not succeed, and then the brain drops down to isoelectric EEG again. One of the earlier devices and methods that we worked with was the auditory evoked potentials, and that was in the early days when I started to work in development of depth of anesthesia monitors in the 90s. That was thought to be the holy grail in terms of monitoring depth of anesthesia, because the hearing is the last sense to disappear, and also because the auditory evoked potential has an anatomically identifiable origin, which means that it's not like the pseudo-electric EEG signal that we record with a passive EEG. So the fascinating part of the AEP is that we can actually identify the specific component. So right after the stimulative auditory nerve and brainstem signal, and then later followed by the middle latency AEP and the long latency AEP. So brainstem auditory evoked potential, middle latency, and long latency AEP. So the times down here in milliseconds is the time after an acoustic stimulus is given to the patient, and this is then the electrical response elicited from the acoustic stimulus. This signal is not directly available in the EEG. We have to extract it. The easy way to extract it is just by repeating the stimulus and then carrying out aberrating. Then we will then be able to extract the AEP. So this in theory and in the textbook looks like a really clean signal, but it is actually quite difficult to get a clean auditory evoked potential in the operating theater, having in mind the amount of electrical noise from other devices which are typically present. So after this introduction, I will speak about nociception and the qNOX. So there are other methods, of course, to monitor nociception balance. The three methods I'm showing here, pupillometry, heart rate variability, skin conduction, they're all based on sympathetic activity. And I think these measures are more indirect measures. So the research that we are carrying out is based on processed EEG and finding a signal from the brain which relates to depth of, to nociception. And if we look into some of the literature, for example, works carried out in this case here with a PET scanner, we can see an activation of the insular cortex during a response to, in this case, thermostimulation. So we can see as stimulus temperature is rising, then activity in the insular cortex is changing. And this was also shown in the work by Richard Weiss, where they were recording fMRI, functional magnetic response, to quantify the time dependence of remifentanil anesthesia in the human brain. So in this study, remifentanil was given to subjects who were at the same time recorded with fMRI. And here we can see clear changes in the insular cortex as well as a function of the administered remifentanil. So this leads to the hypothesis that it is possible to detect nociception balance from the brain. Obviously, it would be ideal if we could record, if we could put the electrodes inside the brain. That's not practical. We will have to put the electrodes on the scalp of the patient and then record the data from further away from where we actually have the most interesting or most correlated signal. But with advanced signal processing, it's still possible to extract and separate the EEG from different brain centers. So in the development of the qNOX, it was based on a large database where we included 1,000 patients with a number of different anesthetics and analgesics, sevoflurane, desflurane, propofol, remifentanil, ketamine, and muscle relaxants. And the qNOX was then developed by classifying the EEG to responders versus non-responders to painful stimuli. So this means that the qNOX is an empirical index. It's not developed based on a specific activity in certain brain centers, but as mentioned before, we obviously position electrodes in order to extract a signal from relevant brain centers. So the qNOX, the final qNOX is then an index from 0 to 100, where 0 is defined as zero probability of response to noxious stimulation and 100% probability of response to noxious stimulation. This is the mathematical method that we are using. It's a quadratic equation where we are inputting different ratios from the EEG and then using burst suppression as well to finally define the qNOX index. So on this slide here, the physiology of the signal transmission is shown where a painful stimulus will give potentially an arousal in the EEG as long as the patient is not covered with opioids or some other analgesia. And this is also described here in this hierarchical model, where we follow the signal, the stimulus from the peripheral nerve, spinal cord, up to midbrain thalamus, and we are then the signal. If the signal reaches cortex, well, then there'll be changes in the EEG and subsequently changes in the qNOX index. So defining then the clinical state versus the probability of response to tracheal intubation, we can then, with the logistical regression, define different ranges of the qNOX, where 0 to 40 is defined as low probability of response to noxious stimulation, 40 to 60 patients unlikely to respond to noxious stimulation, 60 to 99 patient likely to respond to noxious stimulation. There's, of course, a strong overlap, I think, between monitoring hypnotic effect and analgesic effect. So we extract two indices, the qCon and the qNOX, from the same EEG. It can be difficult to define exactly which effect is hypnotic and which one is analgesic. What we haven't observed in several studies is that the qCon, so the index of hypnotic effect, tend to decrease before the qNOX, and vice versa. When the patient is waking up, then the qNOX tends to increase before the qCon. So with that, we concluded that level of consciousness is disappearing before probability of response to noxious stimulation. In the very deep planes, if there are very high levels of burst suppression, the two indices tend to be very similar. So this is the study I was referring to, the study of Humberto Milian and co-workers, published in the Journal of Clinical Monitoring in 2017, where here we see the average of the patients, 140 patients who were included in the study. So it's quite clear that the qCon dropped down before the qNOX, and vice versa. When patient is waking up, then the qNOX is increasing before the qCon. So we could define qNOX also as an index of early arousal. These indices have been implemented inside the Conox monitor. As we see here, the qNOX with its auxiliary parameters, burst suppression, EMG, signal quality index, EEG waveform, and trends as well. The scales are both from 0 to 99, both for the qCon and the qNOX index. If we look into overdosing, then we will see that this is probably one of the more important issues in terms of correct dosing of anesthesia. Delirium and cognitive decline could be the more serious consequence of overdosing of anesthesia. And some of the publications that I've chosen to show here is a very recent one, which I enjoyed very much reading, by Paul Garcia and co-workers, where I highly recommend this article, where there's also a good analysis of what changes could be expected by analgesia and hypnosis in the EEG. So making a two-dimensional plots where we see changes in EEG due to analgesia and other changes due to hypnosis. One of the first articles that was published was this work here, where we were comparing qCon and qNOX to NOx stimulation. So in this study, 60 patients were included, anesthetized with propofol and remifentanil, and the patients were divided into movers versus non-movers. And we saw a significant difference between the patients who moved and the ones who did not move as a response to NOx stimulation. And from that, we could then generate the logistic regression showing how the qNOX is dropping down when the probability of response to either of the free stimuli was getting lower. In this study here, we see a comparison of the qNOX and the ANI, and we found that the correlation of the qNOX to the concentration of remifentanil in terms of prediction probability was significantly higher than that of the ANI. The final study I want to show here is a study where the nociception index was recorded during hypothermia for cardiopulmonary bypass. So both the qCon and the qNOX dropped significantly when the temperature during the CPB dropped down from normal temperature down to around 32 degrees. We can see there's especially the qNOX showed a very marked decrease during the period of hypothermia. qCon dropped down as well, whereas the changes in BIS was less significant. So in conclusion, indices based on processed EEG can predict nociception anti-nociception balance, and the qNOX is our nociception anti-nociception index, which is implemented in the Conox, has been shown to detect response to movement. It is still a new index. We certainly need further studies to be carried out. And with that, I say thank you very much for your attention, and I hope we still have a couple of minutes for questions. I think it's still a very fascinating field, and I think there's still a lot of research that we can carry out in terms of understanding in more detail the behavior of the EEG and the changes in the EEG that occurs during different concentrations of analgesia.
One small question, sir.
Sorry?
One small question. Am I audible?
I can hear you, yeah? But speak a bit louder, please.
Yeah. Actually, you have studied the qCon for consciousness and qNOX for pain. How will the amnesic agents, if we give exclusively, like benzodiazepines, how do they interact? Any studies have been done?
We have been looking into that as well. And there's an effect mostly on the level of consciousness index in that with these specific drugs you mentioned.
Okay, thank you.
Can I ask a question, please?
Yes, certainly.
Yes, regarding this wave of the qNOX, is it the same wave which we see on the bispectral index monitor? And whether both waves are correlated to the median frequency of the power spectral array or not?
There's always a correlation to the change of the median frequency. When the patient is anesthetized, then the median frequency is decreasing, and that decrease can be caused both by hypnotics or by analgetics. And this is the difficult part to separate the two. We're not using bispectral analysis. We are looking into frequency bands. So we see specific changes due to the hypnotics and specific changes due to the analgetics. So by that, we can then define the two entities because the changes are not the same, but obviously there is an interaction. If you give propofol and remifentanil, then the drugs potentiate each other. So it's not that qCon is only reflecting the amount of propofol and qNOX only reflecting the level, the concentration of remifentanil.
Excuse me, sir. When I say the median frequency is the mother frequency for all this monitoring, am I going to be correct in the statement?
Well, what is your statement again, sorry?
Statement, the median frequency. If I get the median frequency, which divides the power spectrum into two equal halves, does this reflect the origin of the bispectral index wave or the qNOX wave as well, or not?
No, these are two different signal processing methods. One method is the bispectral analysis, and another one is the middle spectrum, as you correctly define it. So the mid spectrum is where we see the largest change in that is when we give a hypnotic agent. So we have a decrease in our spectral edge frequency or on the mid frequency. So a clear decrease in, so higher frequency would disappear, meaning that the spectrum is moving to the left. So your mid frequency will then be moving to the left as well. And this is very characteristic for the qCon, for the hypnotic effect. This is not so markable for the portion of the EEG that we analyze for the qNOX index. So these are two different methods, the bispectral analysis and the mid-frequency. And these changes would have to be analyzed independently. I don't know if that answers your question.
Yes, thank you very much.
You're welcome.
I think our last question could be in the chat. There's one more. If you could read it and react to it, please.
Yeah, hang on a second. I need to find the chat. Okay, so the question is, does the qNOX wave the same as median frequency on the PSA? No. No. The qNOX wave is not the same as the median frequency on the power spectrum analysis. So the qNOX is a composite index of more than just one parameter. We are using median frequency as well, but it's so we are taking alpha, beta, gamma, delta waves, and we're feeding these into our quadratic equation, which then means that it's a composite index. The qNOX is not just one frequency, therefore it's not the same as the median frequency. Okay, thank you very much for your attention, and if you have any other further question at any stage, then of course you are very welcome to write me. Thank you very much for your attention.